So, my name is David, and welcome to the academy. So, a few days ago, I was with my students on a different, it was a field trip, and we opened an inverter out of curiosity. We just wanted to see the internal architecture of the inverter and learn a few concepts that we had picked in class. So when we opened the inverter, we realized that the information that had been given on the nameplate or on the specification sheet was not was different from the actual architecture of the inverter. And what we realized was that the inverter had been, the specifications were that the inverter had two MPPTs and it could accommodate two strings independently, and it had two MPPT charge controllers. But when we opened the inverter, we realized that both strings were parallel and ended up into one MPPT. So I told my students, you should also now start understanding how to read and interpret the information on the nameplate, and probably just do a simple it's probably that we could call it due diligence. Just ensure that whatever is being marketed on the nameplate is the actual information or the actual architecture of the inverter. So someone asks, so why is it significant? This is why. Our roofing designs will normally affect a lot of things when it comes to solar installation. Assuming a client has approached you, this client who owns this house, and as a student or as a technician, you've done your system sizing, you've probably determined that now we need a certain number of panels on the roof to be able to generate X amount of power for a particular period. This is now after system sizing. And then your final decision is that you need 6 panels on the roof. But now when you go to the roof, you realize that there is no single stretch on that roof that will allow you install 6 panels comfortably on the same space. So that means you have to distribute your panels across the roof. It could be whichever. For example, if the roof is what we call the gable, you could have your panels on one side, some 3 panels on one side, 3 panels on one side. Or if the roof is like this one, so you can have 3 panels on this side, 3 panels on this side. So depending on the roof structure, I just want you to have that picture in mind, and you can visualize it. You can just go out and look at any other roof and see how you can distribute your panels. So we've learned about the different configurations of panel connections. You can have a series connection, you can have a parallel connection, and you can have a combination of both series and parallel. And this is just to ensure that the intended output is achieved within the time period. For example, if you intend to generate X amount of power within 6 hours, you can have a combination of both series and parallel so as to meet also the inverter input parameters, because some inverters will only start working probably at X volts. So you have to combine your panels in such a way that they generate the enough amount of voltage to power up the inverter, and also enough amount of current to, like a combination of voltage and current, to ensure that the inverter is operating optimally. So when you go to source your inverter, if a roof has been designed this way, you'll have to do an analysis and realize that for this design, I'll need a roof that I'll need an inverter that has got more than one intake point, or one string intake. That is that means that if, for example, this is one string, you have this string going into MPPT number. So this is string 2, this is string 1, for example. So if this is string 1, you have string 1 going into the inverter, string 1, intake point, and that string 1 is connected to an MPPT. Now, this MPPT is separate from this one. That means that during the early hours of the morning, if the sun is rising from this side, during the early hours of the morning, this side is generating optimally, and so this MPPT will optimize the maximum amount of power coming from these panels to charge your batteries for the early hours in the morning. During midday, probably both of them are generating optimally. So both MPPTs will be taking power optimally and charging the batteries. Now, during the afternoon, this side is not generating optimally. This side is. So this MPPT is taking power from these panels and optimizing the entire input to ensure that there's maximum power going into the batteries. The difference is that if you have all this connected together, even in a parallel system, during the morning hours, whatever is being generated this way might affect the whatever is being generated this way might be optimum, but here we are generating below par. So a solar array will only perform, most solar arrays will perform in most cases to the best of the weakest link in the system. So the weakest panel or side will determine the whole output of the entire array. So if this side is weaker than this side will determine how much power is going into the system. If it were one MPPT, like one MPPT, both strings are connected to one MPPT. So this is one configuration. Having two MPPTs or three or even four in the same inverter ensures that you can mount your panels on different sides of the roof, pull down the strings independently, and push power to your batteries or even to the loads optimally at any given time during the day. If you cannot get an inverter that has got that has got more than one MPPT, you can also modify your installation and ensure that you have 3 or 4 different MPPTs independently. You can buy a charge controller independently, 3 or 4, have your panels configured on the roof on all the sections of the roof, so that you can have panels on this side, and even this side of the roof if you can accommodate some, this front side, this side, and have them configured in such a way that you can say these panels and the ones here can be feeding to one MPPT, like outside the inverter, and then all of them now push that power into the inverter. So that's what I wanted to say. Now,